Okay, hello. This is Robert Seacord, and I'm going to talk to you today about secure coding C and C++ and volatile the volatile qualifier. So, just to stay current with what's going on in the world today, I asked Delphi if I should qualify my variable as volatile, and it thinks it's a good thing to do. So that's at least the AI position on volatility. Um, so I'm a technical director at NCC Group. I spend most of my time doing things like this, developing and delivering secure coding training classes in Java, C, C++, C Sharp. I also do code security review, code analysis, and I lead the research team at NCC Group that's interested in reducing vulnerabilities at scale and open source software. I'm also a member of the C Standards Committee. I've been on the committee since 2004, and my first meeting was actually there in Norway in Lillehammer. I also wanted to thank JF Bastian, Aaron Ballman, both of whom helped me out with the contents of this presentation. So here's the agenda. We're going to briefly go over some historical context and then talk about volatile semantics, some work to deprecate some aspects of the use of volatile qualified types, talk about inter-thread communication, shared memory, and some updates to the C23 standard. So here's a use case from early Unix sources that sort of motivated the use of volatile in the C language. And here we've got we've got an address specified by this macro KL, and we want to iterate while we're waiting for the sign bit of a keyboard status register mapped to this address in KL to become non-zero. And the problem with this code is the possibility that the compiler might optimize this. So it might read this, memory location into a register and then, just evaluate that register. And at that point, the register is never going to change value. It's only the process of actually reading this address that might produce a new value. So Volatile can address this problem and can be used to rewrite the loop where we perform a volatile qualified access to reference the memory. Equivalently, we can declare the low byte to be a pointer to volatile qualified memory and access the byte through low byte. And so the purpose of the volatile qualification here is to prevent the compiler from caching that memory, the value in that memory location into a register. So we want to guarantee that it's actually read on each iteration. So when it finally changes, we can detect the change. Otherwise, we would wind up with a true infinite loop that would never exit. So an object that has volatile qualified type can be modified in ways unknown to the compiler, to the implementation, or have other unknown side effects. So the volatile keyword imposes restrictions on access to that object and caching of the object. So in the latest draft of the C23 standard, it says that accesses to objects through the use of LValues or volatile qualified types are evaluated strictly according to the rules of the abstract machine, meaning that basically every read has to be performed and every write has to be performed. So at every sequence point, the value stored, last stored in the object has to agree with what's prescribed by the abstract machine at that time. So in the absence of the volatile qualifier, the contents of the location can be assumed to be unchanged except for aliasing. And so what that means is that the compiler might decide to optimize it, right? So it might decide, well, I'm writing to this storage, but I'm not reading it again, so that's a dead code store, which can be removed. But with the volatile qualifier, it can't be removed because we're telling the compiler that writing to that object might have side effects, and they have to occur. So you have to make sure code is generated to perform that write. So this is appropriate for memory mapped I/O registers. So a static volatile object can be used for a memory mapped I/O register. Compilers have to take into account the relative hardware details on the target system and make sure they implement those correctly when implementing access to these volatile objects. So, for example, the hardware might require that a 2-byte memory mapped register not be accessed with byte operations. You might have to read or write both bytes at the same time. So a compiler would have to assure that no byte operations were generated, even if the source code was only accessing a single byte of the register. So whether or not read, modify, write instructions can be used on these devices also has to be considered, right? Because that would both read and write the object in a single, in sequence, and whether or not that makes sense for that register has to be determined. So because of all this, access to volatile qualified objects is implementation defined, right? The compiler has to know, for example, that the particular register maybe has to be accessed, can't be accessed with byte operations. And because this is implementation defined behavior, all these behaviors have to be documented by the implementation, so you know what they are and how they're performed. So a static const volatile appropriately models a memory mapped input port, such as a real-time clock, right? So you won't write to the clock, but each time you read from the clock, you'll get the current time, for example. A const volatile object can be used to model a variable that can be altered by a different process, but not by the current process. And the cast of a non-volatile object to a volatile type doesn't have any effect whatsoever. You can't cast away the volatility. Sorry, you can't kind of take a non-volatile object and turn it into a volatile object by applying a cast to the object. So to access a non-volatile object using volatile semantics, you can cast its address to a pointer to volatile and access through that pointer. And we'll actually talk about this a bit more towards the end of the presentation today, and what its current status is in the C language. So loads and stores that access volatile memory in the original source code need to generate instructions by which each byte is accessed exactly once, right? It can't be accessed 0 times. It can't be accessed more than once. So volatile can be used, for example, to load and store variables, used for shared memory, for signal handling, and for set and long jump, and other external modifications such as special hardware registers. So the key here is really that volatile is used for things that can be externally modified. So if the source code has a load or store of a volatile operation, these must occur the same number of times in the final execution. So if you have 5 reads and 7 writes, the final execution has to have 5 reads and 7 writes. A volatile operation can't be eliminated or fused with a subsequent one. Even if the compiler thinks it can do it without changing the behavior of the program, just because, again, each write or read is essential. And in fact, if you have volatile qualified object X and you say X equals X, the compiler is required to read X and then take the value it just read and write it back to X. Every read and write needs to be performed. So a volatile operation also cannot be speculated, even if the compiler can undo or make that speculation benign, because the speculation will access the volatile qualified object, and that again can have side effects that the compiler is not aware of. So here's an example of a set jump, long jump program, and in this program we have a variable foo, which we initialize to the value 5, and then we have a set jump point here. And within the set jump, we'll see if foo is not equal to 5, and if it is, we'll print out this string high, and then long jump back to this point here, the set jump point, and retest to see if it's returned 2 or not. And so after this line, we set foo to 6, and then we long jump back here again, but with a value 1. So this isn't going to terminate. It's going to continue through the loop. And so what should happen is that, on the first iteration of the loop, foo is not 5. So we continue executing. We set foo to 6. We jump back, and now foo is 6. It's not 5. So we'll print out high, long jump back to here, and this time we'll exit the loop. But unfortunately, it doesn't quite work like that. So the compiler, of course, is always looking to optimize your code. Typically, that's a good thing. And so what it'll do is it'll look and say, well, for this line, for this code to execute, foo has to be not equal to 5, but it is clearly equal to 5. So the compiler will reach the conclusion that this line of code cannot execute and therefore can be removed. Then it'll look and say, okay, we're assigning a value to foo of 6, but we're not going to read that again. So that's a dead store, and that can also be removed. And the consequence of this is that we now end up with an infinite loop, because we just come down to this long jump with 1 that jumps back to here. It's not equal to 2, so it just iterates for all eternity. So the way this can be fixed is to declare foo to be a volatile qualified object. And what happens now is when the compiler looks at this line, it can no longer say that foo is definitely equal to 5, because we've declared foo to be volatile qualified, and this means it can be changed in a way that's unknown to the compiler. And in this case, this is the change that it doesn't know about, because it's not aware, basically, that this set jump code can be executed multiple times because of the set jump long jump. So by making foo volatile, we prevent this optimization. We prevent this code from being optimized out, and now the code will execute as intended. So for inter-thread communication, volatile object can be used for objects shared among multiple processes. For within a process, most implementations do not insert sufficient memory faces to guarantee that other threads or hardware devices see volatile operations in the order in which they were issued. So it's pretty unclear how to use these weak guarantees in portable code. For volatile objects to be useful for inter-thread communication, updates have to be atomic, as would the reads of those objects. So volatile doesn't guarantee that memory operations won't tear. So a volatile load or read can be observed in could observe partial writes, right? So for example, let's say we were on a 32-bit architecture, and we had a 64-bit value that had to be written or read in 2 instructions, right? So this the high order bits could be written, and then the entire object could be read, and then after it's read, the low order 32 bits could be written, and so we would wind up with a split read where we've got half of the new value and half of the old value, right? And that would not be good. So we had to be concerned about volatile reads and writes being split, being ripped. So realistically, the only reads and writes that will tear is when the hardware doesn't have an instruction that will perform the entire memory operation atomically. So if you have a type like SIG atomic T, that's guaranteed to be readable and writable atomically. But for larger types, there might not, like the previous example of our 64-bit object on a 32-bit architecture, there might not be an instruction that can read and write the entire object at one time. So an implementation is required to touch each target byte once, one after the other in an unspecified order. And that order could change on each execution. The order of volatile operations cannot change relative to other volatile operations, but it can be reordered relative to non-volatile operations. So volatile doesn't imply any observable ordering in the memory model. Atomic instructions will guarantee sequential consistency for data race-free programs. If you have a data race, data races are undefined behavior, and once you have undefined behavior, basically anything can happen. There are no guarantees anymore. So volatile doesn't provide such a guarantee and doesn't imply a memory ordering or any fencing, although there are some implementations such as extensive processors and Microsoft Visual Studio that will provide stronger guarantees. So the instructions are emitted in a defined order, but processors can issue and execute them out of order, and other cores can observe them completely different order if there's no extra synchronization being used. So this will come from, or can come from, implementation guarantees or hardware mapping specifics. So here's an example of the use of volatile for synchronization, which of course is something that you shouldn't do. So in this example, we have a volatile qualified Boolean called G update finished, and we've got a thread. So we've got our first thread that initializes this volatile Boolean flag to false. And then we perform an update of some global data, and then we perform update of some other global data. And once all our updates are finished, we set this volatile Boolean flag to true. Then the second thread is basically looping, waiting for this flag to get set to true, so it knows that these updates have completed, and now it can go ahead and render, the global data. And the problem with this code is that, again, reads and writes of volatile qualified objects can be reordered with respect to non-volatile operations, and so the compiler, is free to relocate this code to before these global variables are actually updated. So the second thread could detect update finish being set to true and decide that these variables have been updated and render them when really they haven't been updated yet, or maybe are partially updated. So again, you don't want to use volatile for synchronization. It's not designed for this purpose. It can be a bit confusing because in Java, volatile can be used for synchronization because they have a different memory model, but in C and C++, it cannot. So basically, volatile is used for external modification. So examples include shared memory, where volatile can avoid time of check, time of use, or TechTown race conditions, which can pretty easily result in software vulnerabilities. Signal handling is another use case where signal can occur at any time in the program's execution. And the optimizer has to ensure that the volatile operations occur even if they are allowed to tear. It's used, as we've already seen in a prior example, in set jump long jump, where set jump can effectively return twice. So volatile will be used to prevent the motion of memory operations around that operation. And external modifications such as memory mapped registers, where the compiler can't assume the memory hasn't changed, or any write to that memory isn't having some sort of side effect. So in C++, but not in C, volatile can also be used to mark an infinite loop that has side effects and is therefore not undefined behavior. And finally, it can enforce control dependencies and prevent compiler value speculation. So as we kind of pointed out already, volatile has implementation defined behavior. So the C standard says that an assignment expression has the value of the left operand after the assignment, but is not an L value. The implementation is permitted to read the object to determine the value, but is not required to, even when the object has volatile qualified type. So what you're getting here is some flexibility where the compiler has the option, but is not required to read the value. So the consequence of that is that this code has implementation defined behavior where A and C are not volatile qualified objects, but B is a volatile qualified object. So we're going to assign, the value in C to the location stored by B, and then we're going to assign a value to A, right? But it's unclear if we're going to read B again in order to assign it, or we're just going to assign it a second time into A. And so there's two independent but valid interpretations of this, both of which access the volatile qualified objects in different ways. And so that's quite problematic, right? Because accesses of these volatile qualified objects could have a meaning, and you want to be very precise in determining how many reads and writes occur and in what order. So basically, this has become a deprecated behavior in C++, and we've proposed also to deprecate it in C. But it's a good idea. Whether or not it's deprecated, you want to avoid that type of code. So if what you're trying to do is you want B to be read after being written to, then it's best to write the code out like this to make it clear that we're going to put the value in C into B. We're going to read B. And then we're going to write that value to A. So this will get you a write followed by a read of the volatile qualified object. On the other hand, if we don't want to read B, we can just assign C to B and then assign C to A. And this will indicate that we don't want B to be read. So this is clear and unambiguous, while this version of the same code is not unambiguous. Okay. So again, this behavior has been deprecated in C++20, and I've written a proposal to deprecate it in C, but the committee hasn't heard the proposal yet, so we're not sure what the outcome of that will be. But this is currently deprecated behavior for C++20, and we'll see what happens for C23. But regardless of what decision is made, right? You want to avoid writing this code because it's clearly ambiguous and could be wrong. So another issue is with compound assignment. So here we've got a structure describing a device, a controller, and we want to either to start the device or we want to stop the device. And so the way we start the device is that we OR this address with this value and then assign it back to the address. And to stop it, we AND the complement with this value and store it back in the value. And what's a little bit unclear about this logic, and here we've put it in, say, a header file that might be included into a C or C++ program, is the fact that these compound assignments, so the compound assignment of that form, it basically is equivalent to E1 equals E1, and then whatever operation is E2, except that it guarantees the value E1 is evaluated only once when you use the compound assignment. But this operation is still a read, modify, write operation. So basically, this value in a controller is going to be read and then modified. We're going to OR it, and then it's going to be written. So we're going to have two accesses of this volatile qualified memory, first to read it and then write it. And it's not always clear, looking at code with these compound instructions, that there's going to be multiple accesses of that volatile qualified storage. The same thing is true of pre and post increment and decrement of volatile qualified types. It's a read, modify, write operation. So if I say, I++, the first thing that happens is we have to read the current value in I, then we have to operate on it or modify it by incrementing it, and then we have to write back the value into I. So the object again might be accessed, will be accessed more than one time. So C++20 deprecates this, and we have our proposal in C to make this obsolete for a volatile compound assignment, and for pre and post increment and decrement operations to be performed on volatile qualified objects. Okay, so shared memory. So here's an example from Chromium where basically we have a GPU process here, and we've got a rendering process here. So there are multiple processes, and the rendering process is going to send WebGL commands to the GPU to execute. And the way it works is that you call a function, and that function will write the command and the arguments into a command buffer, and the GPU process will loop and read these commands from the buffer and then process them. And when it's done, it'll actually then write a result back into shared memory to communicate it back to the rendering process. So there was a CVE for the software with the unlikely number of 1, 2, 3, 4. And so this was in this command decoder, which allowed remote attackers to cause a buffer overflow. And what was happening was that the GL get uniform FB API, OpenGL API was being called. The shared arguments, the shared memory used for the commands is going to be filled with the appropriate function ID and the arguments to that function. The GPU would then read the command and process the data, and then write the return value back into shared memory for the rendering process or the client process. So the vulnerability in this case is triggered by having these two threads running, and one thread, kind of the attacking thread, would continuously call GL get uniform FV, while the other one is going to process the commands and write to the value where the result resides, and the result in this case is a size. So the way this was fixed was with this with this code here. Size result here is just a struct with pod members, and this call here to get shared memory as is just going to return the pointer to shared memory. And so the key to this is really, here's the shared memory store, but this was causing the race condition because this size could wind up changing again before it was used, and then because the GPU had an invalid value because it was changed because of this, basically this TechTown condition, it would wind up with a buffer overflow because it no longer knew the size of the object it was writing to. So the way this was fixed was that the size value is also it is stored into shared memory, but it's also stored on the local stack where it can't be overwritten. But the problem with this solution is that the compiler doesn't know that this shared memory can be externally modified, and consequently, it can perform a lot of optimizations around this, such as delaying the store indefinitely, reusing the stored value, not using result size, or even reusing result size as temporary storage. Because as far as the compiler implementation knows, this memory is not shared with anyone, and no one else is accessing it. So in order to let the compiler know that this is shared memory, you can declare it as volatile, and then it now knows that this can be modified in ways unknown to the compiler. So Volatile Atomic, as we've already seen, Volatile can tear. It provides no ordering guarantees with respect to non-volatile memory operations, and also with respect to CPU reordering. It's required to touch bytes exactly once, and it inhibits optimizations, which is the purpose it serves. Atomic, on the other hand, cannot tear because all the operations are atomic. I can't think of another word for that. Maybe there is one, but so these operations cannot tear. It has a full memory model, but it can require a loop to succeed, and it can be optimized. So ideally, you would think that by combining these two together, you would get the union of properties, but this is not true. So, for example, read, modify, write operations can be implemented by loops, which are going to retry with locked instructions, each of which performs a load and store. So the fact that you have a loop where you might retry multiple times, loading and storing these objects, means that we've lost the guarantee with Volatile that these bytes are going to be touched exactly once. Similarly, we could implement this with transactional memory operations, which might also access the bytes multiple times. The only way really to ensure that you're only touching the byte once is to do these as memory controller operations. So, so if you want to, so a non-lock-free atomic can be volatile, in which case it can tear when you consider the instructions that might be generated. So here we're going to look at a little example where we have a volatile atomic object, which is a small int, which can be which has a lock-free atomic. And we've got a larger struct which contains a 16 element integer array, which doesn't have a lock-free atomic associated with it. And so if we look first at the larger object and we attempt to make a copy of it, you'll see that there's a bunch of instructions that need to be called. So the problem is that, a volatile atomic operation needs to be performed as a single copy atomic across shared memory when the processes can't share a lock. Without this, without having the lock-free atomic, you're going to end up with just a regular unprotected memcopy. So this is not what we want. On the other hand, if we have a lock-free atomic, for example, of this integer, this we're now assured that this lock-free atomic instruction can't rip, and so to get this volatile atomic behavior, you really need to have lock-free atomics for this to work successfully. Okay, so I mentioned earlier some wording changes in C23. One of the problems with volatile, when you read the current version of the standard, which is C17 or earlier versions of the standard, is that volatile semantics are specified to apply to objects declared with the volatile qualifier. So the standard says, for example, accessing a volatile object, modifying an object, are side effects, which are changes in the state of the execution environment, and that accesses to volatile objects are evaluated strictly according to the rules of the abstract machine. So the C standard refers to volatile objects as regions of storage, storing the representations of their values. And so you can see here that, volatile is associated with the object, with the storage of the object, with the data. So, so objects are distinct from the expressions that are used to designate and access them, right? So those expressions are called LValues. It's basically an expression that, when evaluated, is going to reference a particular object, but it doesn't have to mention the name of the access object. It could just be, accessed through a pointer. So if we go back to the original example that we had for the motivating example in the early Unix source code for introducing volatile, we had KL, which was an address in memory, and so there's no way to declare that volatile. So instead, there was an expression where we cast it to a volatile qualified pointer and then access it. So the object itself is not a volatile qualified object. It's just being accessed through a volatile qualified L value. So L values are not mentioned by C17. So volatile semantics could be inferred to not apply to these accesses. And it's definitely a legitimate reading of the standard, although the response to this is, well, this is exactly the reason why these were introduced. So in the Linux kernel, relies on Volatile in its implementation of synchronization primitives such as spin locks and performance counters. So the objects that are operated on by these primitives are usually declared to be unqualified or non-volatile scalar types and just allocated in ordinary memory. So this is for maximum efficiency, so that each object is read and written just like any other object, and so the value can be cached in a register, and various optimizations be performed. So at well-defined points in the kernel, a variable might need to be accessed by more than one CPU at a time, at which time we want to prevent caching. And so on these occasions, these objects need to be accessed through the volatile semantics. So to achieve this, the kernel has two macros, a read once and a write once macro, which basically provides these primitives using volatile semantics. So each macro prevents the compiler optimization by casting the argument to a volatile qualified pointer. So Linus Torvald weighs in on this by saying, volatile is on the wrong part of the system, and see, it's the data that's volatile, but that's insane. Data isn't volatile, accesses to data are volatile. So it makes sense to say this particular access, be careful, but not make all access to this data use some random shit. I'm not sure it's random, but basically be treated as a volatile qualified object. So that's correct, and this was I think the original intent of this all along. It's just that the language in the C standard wasn't very clear. So in C23, we've already modified this language, and this will be found in the latest working draft of C23. And so basically, what we've done is we've taken every reference to volatile object that appeared in the standard and replaced it with language which says, access through an L value of a volatile qualified type, right? So basically, we changed the language in C23, so it's no longer referring to the data, the volatile qualified object, but instead is referring to the access through a volatile qualified L value. So this really should just be a wording change, and it's really designed to make sure the language is in line with what we hope all existing implementations are already doing. So hopefully there are no implementations that actually have to change to satisfy this new language. So in summary, volatility is on the access, not on the object. Well, it can also be on the object, in which case all accesses would have to be volatile, but the access itself can be volatile even if the object is not volatile qualified. There are a number of misleading or invalid volatile operations that we've seen, including the simple assignment, compound assignment, and pre and post increment and decrement operations. These have been deprecated in C++20, along with some other uses of volatile that are unique to C++, but may or may not be deprecated in C. That's still to be determined by the committee. But it's a good idea to avoid these deprecated operations in both languages, for security reasons, because the sort of uses that we've described are prone to misuse, and so you could wind up with a defect or security vulnerability quite easily. And also to maintain compatibility between these languages, because C++ has deprecated this behavior, whether or not C does it. So you want to avoid the deprecated behavior again in both languages. So volatility does not prevent tears, and atomicity doesn't guarantee bytes are only touched once. Volatility overall is about external modifications. It's not about anything else, particularly about synchronization. So volatility preserves the order of memory operations relative to only relative to other volatile operations. So again, it's not generally suitable for thread synchronization. You want to use other synchronization primitives instead. So here's a list of references to various papers. This is the C proposal that the C committee is going to review. Here's various versions of J.F. Bastian's proposal to the C++ committee. Eventually, it was the R4 version, which was adopted, and some additional papers that provide some background material for this talk and for these other papers. So that's it. That's all I have to say about Volatile. If you have any follow-on questions, you can find me on Twitter at RCS. You can find me on LinkedIn. You can send me email. You can call me, but I'm not really good at picking up my phone, so that's probably the worst of the options. But anything else, I monitor pretty regularly, so you should hear back from me pretty quickly. So if there are no other questions, I'm going to end there, and thank you for your time.